Welcome back to the robot mapping class. The lecture of today is on least squares. So we basically moved away from the filtering approaches to SLAM to more optimization-based approaches to SLAM. So this is the new wave of solving the problem. And before going into the details, I will just give you some insights and some notions on what least squares are and how one can solve them in general, and then we'll see next year how you approach the SLAM problem in this way. So, as I said in the beginning of the class, we have these three main paradigms for the SLAM problem. The first two are similar in the sense they're all based on a recursive Bayesian filter. We've seen with the Kalman filter where if we have linear or linearizable systems and Gaussian noise, we can find an analytical way of propagating this, the belief of the states and the map over time. We've seen the particle filter, which is a non-parametric filter. It's much more flexible, but it might be more computationally intensive, or it might be not as precise as the Kalman filter if you don't have enough computation for doing the update and the predict steps. And from now on, we'll see the graph-based formalism, or graph-based paradigm for solving SLAM. And this paradigm basically builds a sparse nonlinear system of equations. And it's called graph-based because we'll have a graph representation, so vertices and edges, that describes the sparsity structure of this system of equations. And given this graph and the equation, we'll see that some properties of the solutions comes from the structure, the graphical structure inherent to SLAM. Okay? This then leads to approaches to least squares to solve the problem, because once we have all these systems together, we can see how to find the solution, minimizing the norm of the error vector. That's where this least squares name comes from. So how many of you knows what the least squares problem is? Raise hands. One, few, okay. But do you know what optimization is? So like if I tell you, let's find x that minimizes a certain function. Do you know what it is? Kind of, okay. So least squares, so let's start from the basics then. So imagine that you want to have a solution of a overdetermined system. So basically means that you have more equations that are known. This basically leads to the fact that you might not have one solution to the system of equations, okay? Because you will have much more, imagine these equations to be lines, and you might have a lot of lines, but none of them intersecting one point, so that you cannot have one solution to these intersections. What one does is tries to minimize the sum of the squared error. So instead of trying to find the point where all the lines intersect, you try to find the point that is the closest to all the lines. Okay? So the idea somehow is something like this. We can probably see it graphically in this way. You can see I have, let's say, a lot of lines that goes like this. And these are all my equations. So it's linear equations, so that basically means there is a line that can be identified by that. And if you want to find the solution to these equations, imagine 1, 2, and 3, this will be probably this point here, no? Because this intersects all the lines, it means that it belongs to all of the equations, okay? It's a solution to all of the equations. But if you now take this line here, there is no way that this can intersect with the others, okay? And the idea of least squares is to try to find the point here, which is closer to all the lines in terms of distance to the line point. That's one way of seeing it in this way graphically. You can also see it, let's say, sometimes also in a form which is analytically says like this. I have my line equation, which is ax equal b, okay? And in here, I have all my lines in there. So you can say a line is the normal vector plus the variable. One line will be something like this. That's the vector, which is the normal to the line, multiplied by the variables. Then you say minus my intercept, so the point where the lines intersect the y-axis, if you are in 2D, equal to 0. Okay, so that's the equation of a line. If now I have a lot of lines, this small a becomes a matrix, this number b, I, becomes a vector, and x is still our unknown that we are trying to find. Okay, so you stack all these equations together, you will have something like this. Now the problem is we cannot find a solution because there might be an infinite of solution, and we try to then minimize this. So we are trying to find an x such that if we take the norm of the residual vector, in this case Euclidean norm, this should go to 0 somehow, no? Which basically means we try to find a minimum, so we're trying to minimize over x this norm here, okay? And that's the least squares because they are the smallest squares. And that's where the names come from. Okay? So this is the classic linear way of describing a least squares problem. Now we'll see what it means when we have nonlinear function and so on. So where did this come from? This comes from Gauss in around the end of the 18th century. And the first time it was used was to predict somehow where the asteroid Ceres was going to, so the whole path of these asteroids in some way. And the interesting thing is that Gauss was also working a lot in geodesy, so in building up maps of the world in the 18th, 19th centuries. And a lot of things that we use in modern SLAM actually comes or can be seen as inspired by the work that has been done in that time. The main difference is that at that time the computers were people with pen that were just writing matrices on a piece of paper and trying to solve this system of equation on a piece of papers. Distributed algorithms where someone was dividing the problem into some blocks and sending letters to other people around the world. Then they were solving it, and then the letters were coming back. So it was a bit slower, but ideally, so in principle, a lot of the things that we've done, we do now, can relate to things done at his time. Also, a lot of techniques used. Okay, so now let's do a bit more formal. Here we have seen how it is when we have a linear system. So we have a linear function here. A is a matrix times a vector minus a vector. But let's say we have now functions, f, I, x, which are generic functions, so can also be nonlinear function. And here we say that x is the state vector, so the variables we are trying to estimate. In the case of SLAM, might be the poses of the robot, the trajectory, the poses of the landmarks, whatever we try to estimate. Z, I are the measurement of the state. So it can be, as we've seen before, for a landmark, for instance, if you know that the landmark has been seen from a certain pose, then we do the usual range-bearing measurements between the angle, between the landmarks and the pose, and this gives us the measurement. This Z is what we get directly from the sensor, and then the Z hat is what we compute using these measurement functions. Okay, so basically this is the same thing we have seen, for instance, for a Kalman filter, where we said Z equal fx. So in the linear Kalman filter, we had that Z was equal to hx plus noise, no? And now, if you go on the nonlinear version, we say it was a function hx plus noise, and this function hx is basically the function we're telling here. Now, the main difference is that we do not have odometry or motion, but we consider everything as measurements. Also the odometry, the control that we do, we will see them as measurements. So before we had something like x at t plus 1 was equal to a function of f at xt and the control plus the noise. Now that's what we've seen before. And now we'll just rewrite these things in a way that says I have this is what I can measure from my encoders or from my controls. And now we'll rewrite it in a way that is u of t is now a function, say f hat of xt plus 1 xt, and we still keep the noise, the additive noise there. Okay? So now basically it's saying that I'm not trying to move the robots around, given the previous pose and the next one and the control, but just try to find the relations between different states. They need to be close to the control. Okay? So once I have all these functions, I basically can put them in the whole framework where I say I just need to have certain function of my state space. In this case is 2 variables of my trajectory, or if there is some other sensor that can measure 3 variables or only 1 variable if you have a GPS, or if you have, in this case, if I also want to put some landmarks in the state space, I can also say x times t, for instance, and the landmark 3. No? So all of this is actually abstracted away by just considering a set of nonlinear measurement functions. Okay? So the goal here is that given these measurements that can be also noisy, we want to estimate the state. So the goal is still the same, it's just that we don't do it incrementally, but we just do it, take all the measurements and trying to find the solution that minimizes something close to that. And we'll see what this something close to that is. So all these F are the same thing I've done here on the whiteboard. Each of them can be any measurements or virtual measurements, and we need to make sure, or we want to make sure that this prediction is as close as possible to the real measurements that we got from our sensors. Now, X can be a position of 3D features. The Z can be coordinates of these 3D features on the camera. For instance, if you're trying to do in 3D what's called structure from motion, so you get your camera and you have some rays and then you move the camera around and you try to find the 3D structure of these points. And at the end you will try to find the most likely 3D position of the features. That's, for instance, one example on where this can come from. Okay? Another example can be that each of these are just odometry or scan matching information, so you only have information that relates 2 poses of a robot trajectory, and you just want to find which is the most likely trajectory the robot did over the time while traveling around. Now, one important thing in least square, if you want to go from the linear to the nonlinear, is the definition of this E with I, which is the error or the error function. No? So if we go back here to this parallel, if we look at the linear case, we have defined the error function. We just put it the other way around, but it's the same. We have defined it, let's say, as this will be our Zi, okay? And this will be our fi of x, no? Which in this case, this function is just a linear function, a times x, and this z is just our b, okay? Now, these are just one row of this, and this is just one row of this one. When we try to stack all of them together, so we have fi, so let's say from 1 to n, the same we do with this observation. We can have from 1 to Zn. We can still write the things in the same way. No? So this, all of them will just be the multiplication of the big A with x, and this will give us a vector of the functional evaluation. Or we can just say I have a set of functions which are this f, and I just stack them into a vector, the output of these functions. No? So that's the parallel between the two. The second thing we can actually do is also include a measure on this space. No? So this is the result of our functions, and for now we're just using as measuring the error. We have this true down here, which basically means is the true norm, or it's the Euclidean norm, which basically just counts distances in, we have our nice Euclidean space, and our distance, if I have a vector here, is just the length of the vector, okay? But we can also imagine that we might have a curved space, so we want to see that this is actually, maybe in this direction is worse to have this, to have an error in this direction rather than the other direction, no? And that's where this omega comes into play. We can change this guy and putting an omega down there, and this ends up in that form here. So when we have a form that says like this, E2 square, this defines a norm, and this norm is E transpose E, in the Euclidean case with the 2 there. If we change the norm, we can also design to have a metric down here, and this basically means we have E transpose omega E, okay? So that's a way of defining a measure on your space. In our case, this will be the uncertainty that we have in our measurement. So basically it's saying the error should count more if I am less uncertain about directions, okay? So that's the idea. This omega is the inverse of the covariance matrix. So if you see the easiest case of this omega, this will basically be a diagonal, let's say with 1, and here we have 100, okay? This basically means that if I have an error in the second dimension, so let's say in the y, this counts 100 times more than an error in the x dimension, okay? And if you look at this from a covariance matrix point of view, that's the inverse. So this will be something that's like this, 1 stays 1, and here is 1 over 100. So basically it says that I'm very certain about this part because I have very low variance there, and I'm not so certain about this part because I have a higher variance. Okay? So this matrix can be anything, so it can also be rotated, stretched differently, and so on. But the idea is that this gives a measure on how much distances actually can change in different dimensions or in different directions. Okay? So once we have defined this, we can define the goal of least squares, which is to find the minimum of this function. And we can see now that this function, we can write it as f, which is our scalar error. We can also define some scalar error terms. So we can say that this one will be equal to our, let's write it here, our fx. The error that we want to try to minimize is the sum over all the individual error terms, ei of x, and these are scalars, this is just one number. And we can define each error as ei transpose, this is now the vector one, transpose omega I, ei, and this is again what we have seen here, no? So it's the same thing. With this norm down here with this omega is E transpose omega E. We have E transpose omega E. And if now we stack all the E together, I'm just doing it to simplify notations on the whiteboard, but if I stack all the E I together like this, and I now take all my omegas in this way, omega 1, omega 2, omega n, and then I take again my ei. Okay, this basically, when I multiply this vector by this matrix and this vector, I get for each of these terms, I sum this, by this, then there is a lot of zeros, so they don't count in the sum, and we end up in exactly these terms here. Okay? So that's a way to write it in very compactly together. So given this error function like this, or compactly written, I will probably write it here for reference, compactly written up here in E x transpose A, Ex squared omega. That's what we're trying to minimize. We can just go and apply what we know about optimization. So we know a few things. We know that this is a squared function. If we now think about the linear case, we know that this is squared. This is linear. So this is a quadratic form, as it says. So basically, this thing is something like this. If this matrix, if the matrix A transpose A is positive definite, is said. So if all the eigenvalues of this matrix are positive, it looks something like this. If all the eigenvalues are negative, it looks something like this. And if they are mixed, there will be something strange in higher dimensions. So you will have something which looks, and now I'm trying to do a saddle point. Yeah, something like this. Not very good, but it's like going down in one direction and going up in the other direction. Okay? So that's what it looks like. But let's now suppose that this is positive definite. So we have a form like this, which basically means we know that this only has one minimum. We can take the derivative of this or of this. We put the derivative to 0, and this is the solution to our problem. We know that this is the minimum that this function can take. Okay? And we can do the same now here. The problem is that you don't know the form of this error function usually, so you need to find a way of going towards the solution step by step, iteratively or numerically. Okay? And that's where the a few assumptions we should make is that we know that we have an initial guess, so we know a value which is close to the optimum, but we do not really know how far, but we know it's kind of close and it's okay. So for SLAM, that can be, for instance, just the odometry. We just consider the odometry and say this is very close to the trajectory of the robot. The initial observations are very close to where the things should be in the world, and so on. And then if we have an error function which is smooth, and by smooth means something that goes somehow like this, so it's not changing abruptly, so it's not something that does, and this is a strange function because it's just completely skipping and going far away, which also basically means that the gradient here is kind of continuous, so that I can go around this function by just following small increments with respect to the gradient. But we don't know where the minimum is, and that can be that there is a nice minimum down here, or it can go up there. No, that's like our cost function. And we can, given these assumptions, we can solve the problem, so we can find a solution for this problem by doing some local linearization and iterative methods. And that's the algorithm which is called Gauss-Newton. I will explain you later on what it means, why it's called Gauss and why it's called Gauss-Newton. But the idea here is that we linearize the error term around the current solution. So let's assume we have an initial guess which is here, for instance. Okay, so we know that's our x. We say our initial guess x0 is here. We come around here, we take a first derivative of this function, so we go around and we take this line. That's our derivative there, which is you can say we can approximate this function with a line locally, and then we take some steps towards down this line because we want to find the minimum. Then we end up at this point, which is x1. We go up and we are here. Now we do the same again. We take the line, we move around, and then we go at x2. Then we go here, we take a step. We might go too far away, so we might overshoot. We go here and we say x3. Then up here, another line, go down, and so on. No? And ideally, we would like to be here, which is our x star, which is the minimum of this function. Now, the problem of the initial guess is that if we have an initial guess which is far away from the global optimum, and there is no way of going down there, you will end up in what's called a local minimum, okay, or local optimum. And the whole point is that you will have, let's say, this area here will be somehow the basin of attraction of this solution. And it basically means you see there is kind of this paraboloid down there. Whenever you are on the downhill sides of this paraboloid, you will end up in the minimum there, but it's very hard to just jump over there because you have to tell the algorithm, go worse, do something worse, because eventually I know that you will do better there. But if you already know that here you will be better, you will probably just initialize in this part. No? So it's kind of very problematic to find out which are a good initialization point. But if you are lucky and you get the initial guess here, then eventually you will end up at this point. Okay? So that's the idea of this algorithm. And it's called Gauss-Newton because it's somehow related to the Newton algorithm for finding the zeros of a function. Don't know, do you know? And does any of you know what the Newton algorithm does? Kind of. Now you take the function, the derivative of the function, and then you try to find the zeros by following this direction. Okay? If you now think of the same thing, but in terms of the optimization point of view. So Newton finds the zeros of, let's say, fx equal to 0. No? He finds the point where this function x is equal to 0. If you now go on a optimization problem where you want to find, I want to now minimize f, this basically means that I want to find the point where the gradient of f is equal to 0. You can apply Newton here, no? And by applying Newton here, what you will end up is that instead of doing the usual update, which is x, I think, if it's wrong, sorry, it should be something like x minus f divided f prime, and then there is some alpha that tells you the direction. Now, this f is this one. This basically becomes something like x at the iteration plus 1 is equal to x at the iteration t minus f prime divided by f second. No? So basically, this is saying that I'm trying to find the zeros of the derivative. So let's do in 1D. So this is now f prime, not the gradient there. Okay? So that's the idea of Newton algorithms. And then we have another algorithm for, there is again an alpha here. Okay? And then we have another algorithm for solving minimization problem, which is instead of a first order, which is gradient descent. Have you ever heard of gradient descent? Okay, which basically instead of doing this, you kind of neglect this part. You just go on the direction of the gradient. Okay, so these things here actually gives you a better direction to where to go because you consider a second order approximation, so a parabola, it goes directly at the minimum of this paraboloid there, as you will solve directly this problem. And neglecting this, you just assume this is a line, and then you just go through the line. Okay? The interesting thing of the Gauss-Newton is that if you try to find the Hessian, so the second derivative of a least square function, you actually can very well approximate it by just considering the second derivative of the error function there. So that's the whole idea in that. Before going to explaining what this is as a, I think I should put the charger. I will now go down and show how you do the Gauss-Newton, and then we can come back to how this actually approximate the Newton steps. So we probably can remove it here. So let me first plug it in. Okay. So one of the main ideas behind all this, the Newton, the gradient descent, and so on, is to approximate the function locally in some way. No? And you can also write it explicitly. And you can write it explicitly by doing what's called the Taylor expansion. No? So we have a function, we now call it E, okay? And we can say, let's see how x changes if I have a certain point, which is an initial guess, let's say, and an increment. So this is to say explicitly, I am at this point of this function, and I want to approximate it locally around this point with some other function. I can do an approximation on the first order, where I say I just take the function I evaluated at x, okay, and then I take my Jacobian, and I evaluate it also at x hat, and then I multiply it by my increments, okay? So this approximation here is a first order approximation, and is actually the line we have seen before, okay? Before we have seen there is this function like this, and then I am at this point, I draw a line, and that's how I'm approximating the function in this way, okay? If you think of this as a one-dimensional function, this will be the f, this will be our f prime, no? And the Jacobian is needed here because our function E is a function that takes a vector as input and gives out a vector as output, okay? So it's a multivariate function from a vector input. Therefore, this Jacobian is what you can also see here down, is the matrix of partial derivatives. So on the first row, you have all the partial derivatives of the first function, so the first element of this error function with respect to all the variables. Second row is the second function with respect to all the variables, and so on, okay? Now we can also do a second order Taylor expansion of this, okay? And the second order Taylor expansion will be the same as the first order, so this one will be plus something that goes smaller than delta x, okay? So it's something that goes smaller than this increment here as an error. The second order is again E at x hat plus the Jacobian at x hat times delta x, and now we can add the second order term. So if you remember the Taylor expansion, we have 1 over n factorial, so it's 1 over 2, because we are now on the second order. Then we have to take the second derivative, in this case would be the Hessian, and this will be a quadratic form. So we have delta x transpose our nice Hessian computed at x hat, delta x, plus in this case a small o of delta x square, okay? So which is an error smaller than the delta x square. These things in 1D will be, this will be f second of x times delta x square, okay? So that's the one-dimensional quadratic form, that's the multivariate quadratic form, okay? This is interesting because this would be the Newton approximation. So if you want to do a Newton step on minimizing a function, you will take something like that, okay? Not for the error function, but for the original function here, the quadratic thing. And the interesting thing is that this action has a form similar to what we'll see later on. Okay, so this is the Jacobian. Now, we can try to expand all error terms, so the scalar error terms, given this expansion that we had there. For doing this, I probably need part of this whiteboard. We can just take the first order approximation, the one we have here, and this basically will be E of, so we have x hat plus delta x transpose omega E of x hat plus delta x. No? That's what we have as terms in our least square problems. This is our norm. And by doing the first order approximation, this will end up to be E of x hat plus j delta x transpose omega E of x hat plus j delta x. No? So this is our first order approximation as we said before. We just replaced it with this. If we now go and expand all these terms, we will have that this times this times this will be a term which is E transpose x hat omega E x hat. Now we have the mixed product, this times this and this times this, and this will be equal to delta x transpose j transpose omega E x hat plus, we do it the other way around, will be E x hat omega j delta x. Now, these two are actually the same. It's one the transpose of the other, and they are symmetric, so you can just write them together, but we'll do it later on. So this basically will be, no, let's do it right now. It'll be plus 2 of this. And then we have the last term, which is plus this part, and this part, which is plus delta x transpose j transpose omega j delta x. Okay, so that's exactly what's written down there. Now we can, that's the expanded version, the latest we have done here. And now we can write them by collecting a few terms. We can say that this one here is our C, that's how it's called there. This part here, okay, no, it's probably, that's, I think it's written with delta x on the other side. It's the same. This one here, it's our B. And this part here is our H. Okay? If you collect everything, recall that this is actually symmetric, this part. So it's because it's basically one number. So one number is always symmetric in terms of matrices. Doesn't change if transposed with itself. So we can just swap this part and this part. And we will end up in what's written down there, which is C plus 2 V transpose delta x plus delta x transpose H delta x. Okay? So that's where we end up in the expanded quadratic form. Okay? And this is a quadratic form, and as we said before, this quadratic form is kind of a paraboloid, and then we can try to look for the minimum on this paraboloid. Okay? So that's the thing we have done. Now this H here, as we said, it's similar to this H here, but it's not exactly the same. And that's where the Gauss-Newton difference comes into play. You can probably write it down here. And is, if we now take let's do from here. Let's just change this as an f so that it's not confusing with the. It's not confusing with that e. So this is just a generic function f, and this f here now is this one, f of x equal. It's the complete norm we are working down there. Okay. So if you now expand this up to here, we can say that the Jacobian of this function, so let's say we have it in the simple case. Let me make it simpler to avoid too much of problems. Let's not consider omega, and let's imagine that this is inside the E somehow. No? So we have a function f, which is equal to another function phi of x, transpose phi of x. Okay, that's easier to to visualize without the omega there. But well, if you put the omega, it's basically the same. If we now take the gradient of this, of f, this will be equal to phi, so 2 times the gradient of phi of x transpose phi of x. Okay, you can imagine it equivalent in 1D. This is a square of a function. Okay, so we take twice the function times the derivative of the function. No, in 1D this will be 2f prime 2fx because of the square times f prime. Okay, and this is exactly what's written down here. Now there is the gradient, which is the derivative. There is the function, which is the function. Okay, you can just visualize in this way. If we now go for the Hessian, so the square of this, basically we just need to derive this guy again. Okay, and you can use the rule for the multiplication, which is probably easier. So you say this is equal to the derivative of this one times this one. So this will be 2. Now let's do the other way around because it's easier to write down. The derivative, so this times the derivative of this one. So will be 2 the gradient of phi x transpose the gradient of phi x. No? So we just have derived this. Plus, now we do the other way around. That's the rule of multiplication. So we take the derivative of this one times this. So we will have plus 2 and the gradient, the second derivative of phi of x transpose phi of x. Okay? So this part here is very similar to this part here. No? You see, it's J transpose, forget the omega for now, J. Okay? So basically this is saying that we are now approximating the Hessian, the real Hessian of the function, with something that's equal to this, and we're just cutting out the second order term, and this is just something, if you also look at it, it goes with the square of the gradient, okay? So, which is then something which is smaller than phi, okay? This basically means that if the function is not too curvy, that's almost 0. So whenever you are very close to something which goes a bit flatter, like a smooth function, or if you're close to the curve, this is very small. And it's actually anyway smaller than these terms here when you change the gradient there. So the more you're going towards the minimum. So basically means if you're quite close, if your initial guess is good, this is a valid approximation of the of your Hessian. And that's where this algorithm is Gauss-Newton. So it's Gauss taking the Newton algorithm, changing it a bit, and showing that for a least square problem, this actually can be done by just considering the gradient of the error function inside the least squares. Okay? So just to give you a bit of history around these things. Okay, so getting back here, now we have this nice quadratic form, and we need to solve it. So we need to find a way of getting the x, or at least in this case the delta x, out of this function. Now, before going there, I've done these things very easy and all stuck together, but is our f, it's the sum of all of them, okay? So you can use the usual commutative property between multiplication and addition, and you can just say, now the c are the sum of all c's, the b is the sum of all the b transpose, and also when you go here, the h is the sum of all the h, okay? Or you can just do it in the stacked version I've shown you before. Now you stack everything together and just compactly write them from the beginning. It's equivalent. At the end, what matters is that you end up with this form, which is a vector of c's, a vector of b's, a vector of, so the matrix of h's here, and this is how you compute the b's and the h given the individual measurements, okay? So either you do individually and sum them up, or you stack them and you basically sum them up by doing vector multiplication. But at the end, you will end up anyway in this sum here. Okay? Is there any questions so far? Okay. So now we have this nice quadratic form, and we want to compute the derivative of this quadratic form with respect to delta x. How do we do it? Let's do it together. That's probably good if you do it together. I'll probably can write it here. It's not needed. So let's take the derivative of f with respect to delta x. So the derivative of c with respect to delta x is equal to 0, okay. Now the derivative of 2b transpose delta x with respect to x, that with respect to delta x is equal to? 2b. Yeah, so we have 2b, so let's say df equal 2b. And now we have the derivative of delta x transpose h delta x with respect to delta x, which is equal to? Kind of. So it depends on how h is formed. So if h is not symmetric, then you have to do it separately. So you will basically end up in plus, let's write it like this, will be, now we are all on the vector size. You will have h plus h transpose delta x, if I'm not wrong. That's because you basically do once derivative of these and times this, and then this times the derivative of this. And in one case, h is transpose, in the other case, h is not transpose. But in the case where we have that h is equal to h transpose, so if h is symmetric, then this one becomes just 2h delta x, okay? So that's in case of h transpose, h symmetric. And h is actually symmetric because it's j transpose j, which is a symmetric thing, and in a symmetric, so it's a symmetric transformation of a symmetric matrix. Now we have omega, which is a symmetric matrix, is our covariance or inverse of the covariance matrix, and then we take a symmetric transformation of this, no? Through the Jacobian, so it then keeps the symmetry as well. Now, so yeah, so this is our nice function here. This is our nice derivative that's close to what we wrote. And now we just need to put this derivative to 0. Okay? So by putting the derivative to 0, we can just saying I have my h delta x minus b equal plus b equal to 0. No? So that's what I want to do. And this is our first order condition for the optimization for the x to be, delta x to be an optimum. We just solve for this, and this basically is equivalent to say that our x is equal to p goes on the other side minus b, and then we need to divide by h. This is a matrix, so we just need to do h minus 1. Okay? And that's how we solve for the increment. Okay, so that's our optimum increment along this approximation, so along this this linear approximation of our error function. Okay? Now, this h minus 1 might be problematic. Okay? It might be problematic for several reasons. One is that it might be very big, so you don't want to invert it, it's very expensive. And the second thing is that this might be not even invertible as a matrix per se. So it might be that some of these eigenvalues are 0, so you cannot really invert this matrix. But before going in the analysis of what we do with H, and this actually we'll do it more in detail when we talk about SLAM, and we'll see that there are a few cases where we need to do something with respect to H, or we need to put something around H to make sure that it's invertible and it's or that we don't have a ill-posed system, is called, where part of the dimension are actually non-constrained. Okay, but this is basically the whole Gauss-Newton algorithm. So we do the first linearization step, where it's basically the first order Taylor approximation of the function. We start with our initial guess, or this will be the x at the previous iteration that you computed. We compute the linearized system, so we just compute our b's, we compute our h, and given that, we compute our optimal increment, which is delta x star equal this, and we just then update the state in this way. This is, there's a lot of flavor in reality for doing these update rules. People do not really so naively update like that. There might be some steps here that you multiply to be adaptive. There might be another step where you actually compute the optimal step again. So you just go somewhere and probe, am I getting better, am I getting worse? There are some that put something around the H to give a certain, it's called trust region. So to basically saying, around this area I can do better. So basically they are adding, for instance, a identity matrix multiplied by a value in there. So instead of doing h minus 1, they do h plus lambda I minus 1. And the effect of this is actually to make the h narrow, okay? Because if you add a lot of values on the diagonal, it's somehow like you're giving a lot of strength to the individual components. So if you look at this in terms of a paraboloid, they just make it narrower, okay? So that you cannot really escape, you can just go down there, you cannot go further away. No? So just make the step smaller in some way. You can see it, you're adding something on something below a number, no? So if before your step was something like Fe divided by n, and now I'm adding n plus something, no? So I'm making the step smaller. That's the same effect that you can see in this way. It's only that it does it in all the directions, and if in some directions there was a 0, there would have been an infinite step that you cannot do, and we just putting a number now becomes again a finite step, no? So that's some of the ideas around that. But let's go for an example first of what can we do with the least squares, if not SLAM. We can, for instance, calibrate a sensor. No? We can do a odometry calibration. So what we have is we want to eliminate some errors that are inherent in the system. There might be that one wheel is actually, it has less air than the other one, so the robot will start to drift on one side, or it might be bigger, or maybe the radius of the wheels that we get from the producer are different. So these are all parameters that we want to estimate. And we just assume that we have a ground truth odometry. Okay, so someone tells us there can be an external system that measures the robot moving around, and or a scan matching or a SLAM system on top. Now, if we have this function fi, that's some simple linear function. So it's just a matrix with a lot of parameters. And we assume that this function takes an odometry measurement, in this case this u, and gives us out the improved odometry measurement there. Okay? So if we want to find now the parameters, which are all these x here of this function. Okay? So these in this case are 9 parameters. So let's see. Let's try to do it together. What will be the state vector in this case? So we have seen we want to find these values here. Okay? Which is the state vector? So the x, 1, 2, okay, so all the x before. Okay, let's just, this is the state vector, so it's all the variables just stacked into a vector that we have. Does anyone want to guess what the error function is? So before we had this nice, we said we have our ground truth odometry, which is equal to our x11, x33, u. Okay, so this is the one we have. This is the matrix to the linear function that maps our data, and this is our output odometry. Okay, so basically for each of these we have a set of equations. Now we have the u star 1, which is equal to the first row of this guy times the odometry, no? So will be the x11, x12, x13 times u, no? And then you will have u2 and so on, no? So if we put them all together, we can have this as our error function. So we have our matrix here, that's exactly the function we had before, multiplied by this u and minus the u star. No? So that's what we try to do. We try to reproduce our ground truth odometry by using our non-odometry and the variables that you are looking for. Okay? So that's it's slightly different than what you have seen here somehow, but just because this one is now a matrix, this one is a vector if you look at this in this way. But you can always just rewrite this x as a full vector and rewrite this u as put the u in the right form such that this the product there is in this form here. But it doesn't really matter because you can always just write it like this and doing the derivative of that. No? So you don't really need to have it in this form, but you just need to have it in a form like this. And then you just go with the Jacobians and so on, and you find all your normal equations. Okay, so the derivative is something like this. And you can see that for the first element of this guy, it only depends on this tree, and it depends linearly on this tree. No? So we just have the three u's there. Because the first u multiply the first element, the second u multiply the second element, and so on. For the second function here, so the second value of this ui, we have this line here multiplies that. So we just repeat the same things here. The same thing for the final function here, the one on theta. It's these three numbers multiplying the vector. Again, we just replicate these three numbers there. Okay? So if you now want to do the linear form like this, you can already do it. because you can just take this one as your A matrix, and then you multiply this by the x vector, where you just put all this one stacked in this way, and you will end up in exactly the same error in the end. Okay? So the first thing here to understand also is that some part of this do not depend on x, and also that since this has no dependency on x, means that this function is actually linear. Okay? Because we know that if the only functions, the class of functions that do not depend on any variables, so they are constant as a derivative, are linear functions. Okay? And since we have this derivative not depending on x at all, it means it's a constant with respect to x, it means we are in a linear form like that. So we don't need to iterate the Gauss-Newton over and over, because we have a linear system and we can just find directly a solution to the linear system. Okay? So these are a few questions for you, just to kind of try to wake you up. So what will the parameters look if we have odometry, perfect odometry? So what will be in your mind, what will be the exact solution? Any idea?
Should be the identity.
Exactly. So the diagonal elements will be all ones, and the off-diagonal elements will be all zeros. No? That's clear. How many measurements do we need to find at least one solution? So we have how many variables? So we have 9 variables, okay? So let's assume independent measurements, okay? So we have 9 variables, okay? With one measurement, how many equations do we have? We have 3 equations, no? One for the x, one for the y, one for the theta of the odometry. Now we have 9 variables, 3 equations. How many equations we need to have to get at least 9 variables out? 9. So how many measurements do we need?
3.
Yeah, exactly. We need 3 measurements for this. We also have that H is symmetric, but we explained it already before, kind of anticipated things. And it's symmetric because it's J transpose J, or the gradient transpose the gradient, so it's a symmetric metric. And the interesting thing is also, how does the structure of the measurement function affect the structure of H? That's a bit more, it's not super easy to know, but we know that if, for instance, if we have measurements like in this way, where we have Jacobians which are kind of sparse, we can say that if we multiply them together, we still keep some of the zeros in our Hessians, for instance. No? Or if we have measurements which are dependent to each other, we are basically having a low rank into the H matrix. No? This basically means that some of the rows are linear combination of other rows, and that's something that we want to avoid in that. Also, another interesting thing is that this H normally is built by doing J transpose J, no? So that's how we do the H. Now, forget about the things in between. Now, these Jacobians have a certain dimension, no? So let's say they have, each Jacobian belongs to R of the number of functions, measurements, let's call them n, times the number of variables we have, no? M. So there is, on the rows, the number of measurements and or the functions, individual functions for each measurement, and m is the number of variables. Okay. Now, when we multiply them together, this basically means that our h is on the number of equations times the number of equations. Okay, so that's the interesting thing. So if we have less variables than equation, this one is always singular, no? Because there will be a lot of zeros in the AH matrix. It's like what we have seen before when we had the vector, which is U transpose. U can be of any dimension, but when we do this, the matrix that results in that has rank 1. So it's all linearly dependent. All of them are linearly dependent. Because the inherent dimension of this product is the dimension of the vector. And the same thing is for J. So the inherent dimension of J, when we do J transpose J, it's this, am I going inside? No, that's M times M. It's the dimension of the variables there. Okay? And basically, this defines the structure of H. Zeros in here puts zeros in H, and low dimensions in here puts low dimensions in H. Okay? So that's the idea on how the measurement function affects the structure of your Hessian there. Okay? Now, any question about how to structure the thing so far? On least squares in general? Is everything clear? Okay. Now, how do we solve this linear system? Before we said we can just take H, we invert it, we multiply by B, but that's not always a good idea for doing that. In practice, there are several ways to do that. One way is if you have a matrix which is symmetric and positive definite, which is luckily the case for nonlinear least squares problem. You can use what's called Cholesky factorization. Okay, we have seen this factorization already when we talked about the UKF. I don't know if you remember that. Now, basically, we divide this H matrix in a lower triangular, upper triangular. And what we then do, we basically solve a set of different systems which are easier to solve. Okay? Another way to do it is by the QR decomposition. Do you know what the QR decomposition is? Does any of you know? So Q is an orthogonal matrix, and then R is an upper triangular matrix. Okay? It's another way of decomposing matrices. This one works with each symmetric matrix, so it doesn't have to be positive definite, or I believe it doesn't have to be symmetric as well, or any other iterative methods. Conjugate gradients is one of them. So you basically just take few variables, take one, so similar to gradient descent, for instance. You can always just take one direction of few variables, go down, and then move around the state space, even if this is a linear system. So you just treat it as few directions to go down in each individually, and then you try to go to the minimum by just following smaller gradients along individual directions. How do we do with the Cholesky? That's the most used one because we have efficient algorithms for computing Cholesky factorization, especially if the system is sparse. And we are in the nice case that this H is symmetric, positive, definite. So assuming now this A, which is our H, is equal to LL transpose, so a lower triangular and an upper triangular, we can actually first solve L times Y equals B. So we just have this Y, which is a virtual variables, and then we solve L transpose X equal Y. Okay? Now, this seems a bit out of the blue, but it's actually something that probably you've already been doing while you were in high school. The idea on this is something like I have my H, this is now equal to L transpose, and this is basically a lower triangular matrix times an upper triangular matrix, okay? Now, when we solve Ly equal B, we are basically saying this one equal B. And this means that the first part will be just something, one value, times y equal y1, b1, okay? So we are basically just saying this one is y1 is equal b1 divided by this, and then we have two values, y2, b2, and now we have y1 already solved, and we just take the second one and we go on and on and on, okay? The same things apply when we do LTX, okay? So basically the idea, and that's why you have done it in high school as well, is that when you compute this decomposition, it's something like you're doing variable substitution when you have a system of equations, no? You just try to say, I now put the first variable equal to something of the other variables, and then I substitute over again and again, no? Like you say x plus y equal 3, then 2x plus 3y equal 4. Now you say x equal y plus something, and then this goes up, and you have y plus y plus y equals something else, and you can get the y out of it. And that's actually what you're doing in this step. And then once you compute this, given the set of variable substitution that you build up, you take these values and put them back into the substitution backwards. No? And that's exactly what you do here. This builds the structure of substitution. This does the substitution down in the chain, so you go up to the lowest value. And this one then brings them back, given the substitution chains you build up. And similarly, if you do a QR decomposition, these things will then be QR, and the idea is again that R is the first system solved, so Ry equal B. And Q, you just invert it, and Q is an orthogonal matrix, so the transpose is equal to the inverse, so you don't really need to invert it, you just do the transpose there. Okay? So these all tricks on decomposition, it's to solve this linear system in a way which is feasible, computationally efficient, and also numerically stable. Because some inversion with low numbers will bring 1 over a very small number that explodes. Now I can just go go above the numerical resolution of your computer. No? Or the problem, for instance, is if you have one of them very big, one of them very small, you never find a range in your numerical, in the number of bits that you can store numbers, that is able to handle all of them. So either you lose precision on the low end or use precision on the high end. So there's always been a problem there. Most of the time you will just lose precision of the low end because you need to have to keep the big number, and the lower one will just become 0, even if it's not 0, but it's just like imprecise. No? So that's a summary from the Gauss-Newton. So we just seen that we can, if we have a problem on this way, so like a least squares problem, we can, and it's not on the linear case, so it's on this case, in the nonlinear case, we can actually find the x that minimizes this norm here by an iterative procedure, where we start with an initial guess, we linearize our error function around this initial guess, we then compute this quadratic form, which is written in here. And once we have this quadratic form, we can just go into classic optimization for a quadratic form. We take the derivative of this, we set it to 0, we find the next step, and we solve the linear system associated with the putting the gradient to 0, and we reiterate over and over. So this gives us a new initial guess or an update on our state variables. We then relinearize and repeat over and over. But how does all optimization things relate to something that we've done before? Now, before we always said we need to find the belief of the state space, we need to find a distribution of our variables, and now we're going in something completely different where we start writing some strange things on the whiteboard and say, let's find the minimum of this. No? There is actually a relation between least square estimation and probability theory, or like estimation theory. One of that I already partially mentioned when I was talking about the Kalman filter. So the Kalman filter has been developed originally in a way to solve iteratively this problem here. Okay, it was made in a way, how can I solve this if I don't want to build up the system of equations, but just take one equations at a time. Okay, and you can prove that the Kalman filter, actually the solution that the Kalman filter gives you in the linear case is exactly the solution to this problem, to a least squares problem. Okay, then people built up a more probabilistic version or understanding of the Kalman filter with when considering this whole state update in terms of distributions, the Gaussian, the integral, and so on. Okay, so but how do we go there? Let's step back and let's say this is what we wanted to do so far. No, like our usual recursive estimation problem. We have the state vectors from 0 to t, we have our observation, and so on. And when we use everything, so Bayes rule, independence assumption, Markov, and so on, we end up on a certain prior over the first variable, so where we believe the system is at time 0. We have our nice motion model, okay, and we have our nice observation model. And we are considering now the full trajectory, so there is no integral over the previous pose, just the full estimation in this way. If you now take the logarithm of what we've seen before, we end up in a constant, which is the logarithm of the normalization factor in some way, plus the logarithm of p of x0, plus the sum of the logarithm of these two terms here. That's because our nice product becomes a sum, our product of these two terms becomes the sum of the corresponding logarithms. Now, if we now consider that this is a Gaussian distribution, so this is Gaussian or normal distributed, and we also consider that the motion model is normal distributed and the observation model is also normally distributed, we can just substitute the normal distribution and take the logarithm, and we'll see that this is equal to a constant minus a quadratic form. Okay, that's our nice normal distribution. If we remember, is always this nice, let's do 1D, it's 1 over when it's like, let's just take the normalization, the square root of the sigmas, and then we have e minus 1.5, and then we have the quadratic form, which is x minus mu transpose sigma minus 1 x minus mu. Okay, so when we take the logarithm of this, that's the logarithm of 1 over eta plus the logarithm of e, which is just the exponent there, so this plus becomes a minus because it's here, minus 1.5 x minus mu transpose sigma minus 1 x minus mu. No? So that's what we have here. So now I'll get back this and we map to what we've seen before at the beginning. We can call this the error terms, for instance. We can call the sigma minus 1 our nice omega. This is again the error term. And this product here is the scalar error term. Okay? So basically, if we now assume that everything is normally distributed, then we can easily say that whenever we take the logarithm of our posterior, we can end up in a sum of a lot of these quadratic terms. Whenever we have, we can have that instead of mu, there will be the nice predictions, our function that predicts the observation. Instead of our x, we will have our nice function. So instead of our x, we will have our function that predicts our observation. Instead of mu, we will have our observations, and that's where we can map directly to the more general case of nonlinear least squares. If we go back to the trajectory, given the observation and control, we basically have one error term for the prior of the initial pose. We have one error term that belongs to the odometry here, and we have one error term that belongs to the measurement. And we will then also sum all them up together. So if you now want to say I want to maximize the logarithm of this, that's also equal to minimize the negative of that. No? So whenever we maximize something, if you just take the negative, we can minimize that. And so minimizing the negative log of this distribution is equivalent to a least squares problem. Now, maximizing the log of a distribution is actually the same as maximizing the likelihood or finding the mode of the distribution. Okay? The reason is that the logarithm is a monotonically increasing function. Okay? So it looks somehow like this. Now our logarithm is something that looks like this. Okay? So if for now I take anything inside the logarithm, I will always be that whenever this value grows, okay, which will be our p in that case, also our logarithm grows. So the maximum of this will be the same as the maximum of the logarithm of that. And whenever our things down comes back, then the logarithm also will go down. So that basically means that the only thing that the logarithm does is kind of changing the relative values of the function at different points, but not their ordering, or not which point is bigger than which others. Okay? And that's because it's a monotonically increasing function. So therefore, we can exploit the properties of the logarithm that puts all this exponential into quadratic form, all the products into sum, and still being able to say that minimizing this is equivalent to find the mode of the distribution or the maximum a posteriori of this posterior distribution. No? So, and this is the connection between these two elements. So basically that's something to remember. Even if we are minimizing something, we are still doing some, we are still considering the noise, we are still in the noise framework of probabilistic estimation. And that's because we know that if we minimize the squared error, we are actually maximizing the log likelihood of independent Gaussian distributions. And if we put a prior terms here, we're actually maximizing we're taking the maximum a posteriori of the whole posterior distribution. Okay? So to summarize, unless there is some other question around, but we can also do it later on, what we've seen is that what is a least squares problem? How can we actually minimize the squares of functions and what it means minimizing this kind of form here. We have seen that Gauss-Newton as one algorithm for finding the minimum of a nonlinear least square problem like this. We have seen also that the Gauss-Newton is an approximation to a Newton algorithm where the Hessian, so the second order of the function we are minimizing, is approximated by just taking the first order, so the first order Taylor expansion of the function inside the squared norm. But we also seen that this is actually using linearization, so we need to have an initial guess. We need to have an initial guess which is close to our optimum, so that when we do down on this linearization or this linear approximation of the function, we are reaching a good optimum. And we've also seen that this minimization on the least squares is equivalent to a maximization from a posterior distribution point of view. So we put some bridges between optimization problems, optimization formulation like this one, to a probabilistic formulation in terms of estimating the posterior distribution. It's also a very popular method. It's used in a lot of discipline, and if you don't know how to find a minimum, or if you don't know how to, whenever you want to reconstruct something, or whenever you want to find a function that approximates something else, or it gets close to something else, least squares is probably the first thing that comes into mind to try out, to see what happens. So to see if you can find a reasonable solution to your problem. If you want to have a bit of literature, if you want to know something on least squares and Gauss-Newton, it's basically everywhere on Wikipedia. Any calculus on optimization, but also beginning of so first year university or algebras and so on, or Wikipedia for a summary. If you actually are interested in more tools on optimization, talk to me, send me an email. I can probably find out few references of something which is a bit more advanced. So the whole idea I was telling you, when you put the identity matrix or how you do line search and all these things, I'm happy to share the knowledge. If you want to see the relation to probability theory with respect to least square and probability theory, that's written in the book. But essentially what you need to know is this the magic that the logarithm does. Now, like you take the logarithm, it ends up in a quadratic form if you have Gaussian distribution. So that's the main thing you have to remember about that. So that's it for today's lecture. And if you have questions, yes?
Those quadratic problems usually have problems with outliers because
Mm-hmm.
the arrow is going quadratically.
Mm-hmm.
Is it a problem too in robotics? Do we have to do with that usually?
Yeah, so you're asking if outliers create a problem in here. Yes, they do, and it's a problem for robotics as well. What we normally do is we try to get rid of them. And we'll see later on in a few lectures there will be something on robust estimation and outlier rejection. But basically you either have an external mechanism that prevents you to having them, or that does some external checks, or you can include in here, so instead of having the error function, instead of being on your real measurements, it's a robustified version of that. So basically, I will just give you some small preview in there, but basically what you're doing here is something like I'm doing a row function of my error function, okay? So that's the typical least square things that you do. Your row function is now this, okay? You can now extend and have some different shapes. Now, this basically tells you that my function looks like this. So whenever I have something which is very far away, this is very high because it will be somehow there. No? And you can change the behavior of this by changing the norm you're working in. You can take, for instance, the one norm, which basically it's something like this. This is just lines. This is wrong. Now, so basically, the further away, the same distance, now you have an error that's that big, and in that case, you had an error that was that big, so you attenuate that. Or you have something that saturates, now that goes here and then. So that's the whole idea. Whenever you are far away, you try to kind of put down the effect that those values have on your minimum. Each of these has different properties, good and bad, of these functions, and it's really somehow a magic in tuning them and knowing which one is good for your problem. There are some rule of thumbs, but we'll see more in details later on. Is there any other question? No? Okay, then that's it for today. Merry Christmas and Happy New Year. I think we're not seeing each other before the holiday starts, so wish you very nice starting of New Year. And we'll see each other the 18th, if I'm not wrong. And there will be 2 or 3 exercises more, I don't know. So the one on the 7th, so I think the one right before Christmas, which is 21 or 22, is not taking place of the exercise. The one on the 7th, I think it's also not taking place, so that week. and it's taking place the week after. And I'll be back on the 18th for the lectures. There was a bit of, I had to reshuffle a few things around for being sure to finish the program in time. Okay? Good.